Are you guys able to see my screen?
This is okay.
Yeah, sorry.
Yes, visible.
Okay, okay. Okay, good. Thanks. So, let us start our 36th lecture on control of active powers. And we saw in the last class, let us just quickly recap in the last class. And if you have any queries, you can ask. So, we started with isochronous governors, and we saw that, okay, if the generators means if only one generator is there in the network or in the system who is trying to settle the load change, then he can easily maintain the speed and the frequency, and he can easily balance the load. But if, let's say, there are more than one generator who are trying to satisfy this load change, then obviously there will be some oscillations, and eventually the oscillations, I two things can happen. Either the oscillations can die out and stabilize the system, but it will take a very long time, or because the long time is they are taking a long time to stabilize, because the continuously loads are changing. So there could be a situation that because they have not stabilized before the next load change, so they might go into instability or unstable situation. So therefore, we added the droop characteristics on that synchronous governor, that this R will actually ensure that the generators do not compete with each other to stabilize that load. Instead, all the generators will be competing in such a way in based on this R value, and this R value can be set by the plant operators and their choice, how much they want their generator to change, because this R value will actually affect the it will change the valve openings of the turbines. And obviously, if you continuously, because loads are continuously going to change, and that will eventually change the frequency, and that will eventually change the speed of the generators, and that will eventually change the governor actions and eventually the valve opening. So as you often do those changes, there will be a risk of wear and tear, and a generator might suffer high maintenance cost. So therefore, it is the choice of the plant operator how much he wants to keep, and yeah, he can decide on that value. And typically, generally, because in India, I can tell you that it is regulator has given some standard that you have to ensure that you are keeping some portion of R, means they cannot keep it zero or so. So they have to provide a R value for uh, and there is some regulation on that. So yeah, so they cannot deny that we will not provide it. So it is based on the regulation. They have actually, Indian government has given a criteria based on the size of the generator. If the size of the generator is huge, then they are mandated to provide some R or some regulation. And if the size of the generator is very small, then they are free. They do not have to provide R. So it is based on some size. I think it is more than 100 megawatt. I'll just cross check and let you know. You can easily just search and find that out. Okay, so then we moved ahead and we solved this numerical example where we saw that how the change in load eventually affects the change in the generation value, and how the change in frequency leads to the increase in the generation by a small value to settle down the load, and this happens because of the governor. So basically, idea is, as soon as the load reduces, the frequency starts or rather, let's take load increases. So if, let's say, if I say that the load value has increased, because of this the frequency will drop, and because of the frequency dropping, it will keep on dropping, because as the load has increased, if you do not disturb or do not change the generation value, it will keep on dropping. So therefore this governor action or regulation or speed droop characteristics, because of this, the PG value or the P generation of the generator increases by a small value, which eventually stops the frequency drop. And this frequency is not at nominal value, it is still at a value which is not 50 hertz. So this frequency is not equal to 50 hertz. So this is the value which is different than the nominal value, which is 50 hertz. So it actually just settles or stabilizes the frequency to a value, and stops the change in the frequency. We later on we saw that, okay, if the load, if one generator is there, then if let's say multiple generator is there, then how they interact with each other. And this is here I have explained you how different regulation generators, if they are combined, if they are working in parallel, then how they will be supporting the change in the frequency or change in the load. Here also we saw one numerical example, and we saw that, okay, this type of if regulation is there, then the load share you can decide, and also you can see that how much maximum load change it can handle. So if beyond a particular load change value, because of R, the generators are limited and they cannot provide more generation, although they have the capacity available, even then they will not be able to provide the generation value. And the generators which are actually getting hit at its maximum limit, those generators will actually automatically cut off, and they will not be participating in R, and they can immediately stop the power plant from changing, or stop the governor from changing the valve position. So basically it is valve is wide open, and it is full steam and full hydro is passing through the valve to the turbine. Right, so this is what we did in the last class. Any queries till now? Okay, if no queries, then let us go ahead and see one common observation. What you can say here is, when we were calculating in the previous numerical also, when we were calculating the regulation, we were always calculating. So this is the P max, this is 0, and this we were always keeping as 50 hertz. Right. Now you must you may be curious here, that why 50 hertz? Why the starting or the nominal value, when P is 0, at that time, why we are keeping it as 50 hertz? Why can't we increase that value, so that whatever is the operating point, that becomes as 50 hertz? Right, can we not do this? So this will actually simplify the issue, and the frequency can be adjusted in a much more better way. Right, so this diagram here, what you are seeing in the left here, earlier we gave this speed reference, and then we were getting this delta omega R, and we then added this R, which is a droop characteristic. Here you can add this load reference point. This load reference set point, you can add this, actually in shift this up and down. So basically R gives the slope of these lines A, B, C, and this load reference set point actually in vertically shifts this line up and down. And this load reference set point is again given by the plant operator. He can choose that value according to his choice. So basically, let's say if in the previous example what you have seen, there you saw that one of the generator was having the capacity, but still it was not able to provide its full capacity because the of the regulation. So in that case, what you can do is you can increase the set point, load reference set point, and then you can control the generators. Are you guys able to visualize that thing? So So basically, here the idea is whatever is the regulation, but the regulation is fixed. But here, by adding this load reference set point, you can increase this. So at 0, we were discussing that it is 50 hertz, but with this set point change, it will no more be at 50 hertz. So at 0, it can be either 51, 52, 53, any value you can set at. So here this diagram what I have given, this is for the US based system. So that's why it is not taking nominal as 60 hertz. Right, so but you can change that value. So for example, here in US it is 60 hertz. So you can see here we were taking always the A curve where it is starting from 60 hertz, or for our case we were starting at 50 hertz. Now what you can do here is increase this load reference set point, and then you can see that the 60 hertz is coming at 50% of the total power capacity. Or you can further increase the load reference set point, and you can see that the 60 hertz is coming at maximum power capacity. So you can play around with it based on the situation. Let's say if the frequency is rising, so you can change that load reference set point to settle at a higher frequency. And if let's say frequency is reducing, then you can reduce it to give more range for the R to play. So I hope you are getting the logic that how this different R set points will play the logic. So you can easily expect how various range of power plant for various range is there available with the power plant operator, and he can play and he can tell its generator to operate within this range wherever the frequency and the load change is happening. Based on that, wherever range or wherever it converges, it can settle to that value. Right, any queries here? Okay, so now I told you that okay, droop characteristics actually work in a very smooth manner. We saw every time we were seeing that the line is horizontal, and it is decreasing in a slope, but this is the ideal characteristic. So this characteristic is the ideal one, right? But in practice it is not obviously that smooth. So let's say if you talk about steam units, so you can see the second curve which is having this multiple jumps. So this multiple jumps is coming because of the valve operation. So in the steam plant, the valve operation is very smooth. It is not basically if you open the valve immediately, more steam will pass, and obviously it's a steam is a gas. So because of that, it is more volatile and it can work fastly. So basically, the to converge to a particular value, it can take more oscillation. So therefore, a small valve opening will also give you a jerk in the turbine, and as soon as you open a bit more, then the more jerk will be there. So that's why the the smoothness is even less in the steam unit droop characteristics. If we talk about hydro generators, it is more smooth because obviously water is it in a liquid state. So liquid state is less volatile than the gas state. So here you can expect lesser jerk. And also basically as soon as you open the hydro turbine valve, so the water starts flowing at a very small rate and then gradually increases the speed. But this is not happening with the steam. So that's why it is having a jerk, but it is just one time jerk, and one time jerk you can settle down the value. So, or rather you can say the lesser jerk is there in the hydro turbine valves. Right, so any queries so far? Okay, so let us solve one numerical and see how. Achha, okay, let us before that numerical. Let us see this. Okay, I forgot about this. Okay, so basically, right now we were all discussing about a single generator. So we were having just one generator till now. We discussed that this part we were discussing, right? Earlier we were discussing this that. So here delta PM, here delta PL, this is plus, this is minus, this we were discussing till now. Now, obviously, there will, in practice, on a practical system, there will not be just one generator, there will be many generators which will be contributing for the frequency change and the load change. So here from this diagram, you can see here that there are various generators, many generators are there, and all these generators in combination are trying to satisfy the load change. And eventually the obviously if there is a load change, then there will be some damping factor because of the load change. There will be change in the load, further there will be change in the load based on the change in the frequency. And this M equivalent is basically the inertia constant of all the mechanical machines. So how do we get this value? So you can see here the change in frequency, we were always discussing that R is minus delta F by delta P. So you can just take the value in terms of delta F will be delta P by 1 by R. You can write it this way, and here they have written in this fashion. So this is the formula how we get the value that for all the generators the regulations can be added here, and plus D, because D is the damping coefficient for the load change due to the frequency. So you can say here that REQ, or you can make it in a generic sense that REQ is the equivalent regulation or the droop characteristics in the combination of all the generators who are trying to satisfy this load change, right? And here there are three basic terminologies, that this beta, which is nothing but the blower part, this below part is beta 1 by req plus d. This beta, you can say it as a frequency response characteristics, the way the frequency will change based on the change in the load. And 1 by beta, you can call it as a regulating response characteristic. So it is just the terminology is what they have given. So it is similar to the logic of R and 1 by R, that logic they are giving here, right? So if, let's say, if I give you a question that there are multiple generators who are trying to satisfy this load change, I hope you can easily solve now using the same concept what I have shown you before. So you just have to calculate the R equivalent of all the generators, and then you can solve this problem. Also, let us see how the load change is observed. So for example, let's say, just see this situation. So there is a generator, there is a load, and which has some dependency on delta F, which is basically the load is dependent on frequency. Now what happens if, let's say, if I close this switch, or basically I have increased the load, so this delta PL, that is the load I have increased. Now if I increase the load, what will happen? As soon as you increase the load, the frequency starts dropping, right? So basically, as soon as I have increased the load, if just see the left hand of this diagram, as soon as I have increased the load, initially let's assume the frequency was at F0, and now as the load has increased, the frequency from the generator has started dropping, and because of which the generation, based on its droop characteristics, it has started increasing its generation to satisfy that frequency. And also, as the frequency has started dropping, the load has also started reducing because of the drop in the frequency. So eventually, if you will see the total load change, or the net load change, I would say the net load change is actually the summation of the delta pg and delta pd, or the difference rather, not summation, it is the difference of this two value. So basically, because the net load change will be less, because delta PL is more, but because of the drop in the frequency and drop in the frequency dependent load, the net load change will be less. So delta PL is equal to delta PG, that is the increase in the generation because of the frequency drop, and minus delta PD, because that is the increase in the decrease in the frequency load because of the drop in the frequency. So eventually, you know that the delta pg is equal to delta f by r minus delta f by r. This we were always looking at. And even load, we know that it is d delta f, so you can write it this expression is minus 1 by r minus d delta f, and eventually you can calculate that delta f is minus delta pl by 1 by r plus d. So this is the expression, and here you can add this. If let's say more generators are there, then you can easily calculate the equivalent R of all the generators and eventually satisfy the change in the frequency. So this diagram is for the load increase. Now if I, let's say that load decrease, then what will be the diagram? Can anybody quickly help me in drawing that? So initially, let's assume it was F naught, and now let's assume the initially switch was closed. Now I am opening the switch. Let's assume I am opening the switch. Now what will happen? That means I am reducing the load. What will happen if I decrease the load? This was the case when I have increased the load. Anyone?
If I think if you reduce the load, frequency will be increase.
Good, good. Yes, frequency will increase.
That, we have to make damping.
We have to make
damping.
Yes. So D, what will happen? So what will happen to the PD, delta PD? What will happen? It will
PD will be reduced.
Delta PD will increase, right? Because the frequency has now increased, so the delta PD will increase. Instead of dropping, now delta PD will increase.
Yeah.
Right. So delta PD will increase to some value, and also oh sorry, I made it in reverse sense. Wait. So delta PD will increase because the frequency will increase, and then the generation will actually reduce because of this R, and it will try to settle down at a particular value. Right. So the diagram will work in a different sense, in the reverse sense. So you can just quickly tell me in the next class how exactly the derivation and the formula will look like. Okay, I'm leaving it up to you, and I'll ask this in the next class. Okay. Now let us see and solve this numerical example quickly, how this example will work. So here the question is, an interconnected power system has 1500 megawatt at 50 hertz, right? And the frequency change is taking for 2.5% for 1.5% of the load change. Now you have to calculate the steady state frequency if a 200 megawatt of industrial load is tripped, right? So the load is reducing by 200 megawatt. Now how to calculate this? Anyone can help me out? What is the formula? We just saw that formula is minus delta PL by 1 by R. Sorry. 1 by R plus D. Now here load drop is of 200 megawatt. So this will be 200 megawatt. 1 by R. R is assumed to be 0.005. Now what is the value of D? What is the value of D here? So the D value will be, we know that D is basically delta P by delta F, right? We say delta P is equal to D into delta F. I just took this down. Now what is the change in the load? So it is, and it is saying that 1.5% of load change will be, so the load is, net load is how much? It is 300, sorry 1300, because 1500 minus 200. So this is the change in the delta P, and the remaining frequency will operate at this value. And delta F, it is saying 2.5% of 50 hertz, right? Assuming that the nominal frequency was 50 hertz. Now can you tell me what is the value here? So this will go away, this will go away. 13 into 1.5, 65.56. What is the value of D here? 19.5 divided by 1.25.
15.6.
15.6, right?
Yes, sir.
So it is 15.6 megawatt per hertz, right? So what you have to do here, just keep the value here 15.6 and calculate this delta F value.
0.927.
0.927 hertz, right? So now the net steady state frequency will be 50.927 hertz. Because the load has dropped, that means the frequency has to increase. Any queries here? Is the question clear to everyone?
Yes, it's clear.
Okay, good. Now let us see another question. Just let us read the question for a minute and then let us start writing or start solving. Assume that a power system has a total load of 1260 megawatt at 50 hertz. Right. Now the load varies at 1.5% for every 1% change in frequency. That means D is 1.5. Now find the steady state frequency deviation when a 60 megawatt of load is suddenly tripped, or basically load has dropped. Now there are two parts of the question. The first part is there is no speed control. Let us see these questions one by one. Okay, and this neglect the effect of transmission losses. We are not considering the losses because we are assuming that the generation is equal to the load. Now let us just read the first question first and then go for the second question. So basically you have to calculate the load frequency change, steady state frequency deviation, when a 60 megawatt of load has dropped. And the first part is there is no speed control. What do we mean by there is no speed control? What is the meaning of no speed control?
R will be not present.
Sorry?
R not present in calculation.
Yes, R will not be present because no speed control means there is no regulation. Basically, generator will follow the load. Wherever the load goes, generator will follow that, irrespective of the frequency. So that means if now I have to calculate the frequency change, the formula will be the same, delta PL. Here instead of 1 by R plus D, we'll just write D because R is not there. There is no speed control. So that means there is no concepts of droop here. Right. So now the load change is minus 60. What will be the value of D? Now let us calculate the value of D. D is delta P by delta F, the same way. Delta P change in the load at 1.5 by 100 into the 1200 because 60 megawatt has lost.
Okay.
Sorry. Come again, please. What is the value of D here? So this will be 12 into 1.5 will be 18 divided by 1 by 2.5. What is this value?
36.
36. What is the dimension? It will be megawatt per hertz. And this value you have to put here. Now tell me what is the delta F?
1.66.
1.66 hertz. So basically F will be, because the load has dropped, that means frequency has to increase, that will be 51.66 hertz. This is the steady state frequency and the deviation is 1.66 hertz. Clear? So whenever we say there is no speed control, that means it is there is no regulation in the generator.
Sir, what is the value of D mentioned in?
What is the value of?
D equal 1.5.
So D equal to 1.5, this is in percentage.
Oh.
It is in percentage. So basically you have to calculate. So actually you have to see the dimension here. So earlier what we were doing, we were calculating everything in per units. Then you can use this value. But here we are using everything in the actual. So then you have to convert everything in the actual values.
Okay.
Right, yeah. And mostly it is better to convert everything in the actuals. Here it is more logical, but not in the OPF sense. Okay, now let us see the next part, the second part of the question. So the second part of the question is a bit of a big question. You just need to focus for a second. So basically it is saying that system has 240 megawatt of spinning reserve, which is evenly spread among 500 megawatt generation capacity with 5% regulation. So basically now regulation is there with a 5%. based on this capacity, right? So we have to see this capacity later on. And it is saying that all other generators are operating with valves wide open. Basically, if valves are wide open, that means other generators are already operating at its maximum limit, and you cannot touch those generators. Those generators are already operating at its maximum limit, so we cannot touch those generators. Now, it is also saying that the governors has some dead band. Dead band means it can, here it is saying it is 80%. So that means whenever the load is changing, it can only operate with a 80% efficiency, you can, in a simple sense. So that is a dead band, that it cannot operate if the load change is lesser than 80%. So it is of that sort. Right. Now, is the question clear to everyone? We have to calculate the steady state frequency deviation in this situation when the load has dropped by 60 megawatt. So to calculate the frequency here, now because there is a regulation is there, so there will be a factor of R. Now minus 60 here, 1 by R. What will be the value of 1 by R? How will you calculate the R value regulation? It is not directly 5%. You have to calculate it. So R we calculate right. R is delta F by delta P. Now here delta F is 5% change in the frequency. So 5 by 100 into 50. Right? Now below delta P. What is the delta P here?
$1,440.
See here, the other generators are operating at valve wide open, so you cannot control those generators. So we have to ignore those generators, and you also need to consider this 80% fact. 80% of the governor respond. So this delta P will be, so initial, because we are ignoring the losses, I told you initially that the losses are ignored. So basically initially the generation is 1260. So because that generation will be equal to the load, plus there is a 240 of reserve. So total will be how much? It is 1500. Right. Now in this 1500, it is saying that only 80%, basically this is the total generation, and in this only 80% is operating for the governors. So only 80% is operating for the governors. So 80% of this will be 1200. Right. So delta P will be 1200 here. Clear?
What about the load? 60 megawatt load.
Yeah. So 60 megawatt of load will come later on. It is affected in D, not in R. It will play the role in the D because the load change only affects the D part or D delta F. The load change do not affect the regulation part, because load change will affect the frequency, but it will not inform. Basically, only when the load generator outage has taken place. There can be two outages, either the generator outage or the load outage. Here it is, we are talking about load outage. So whenever load outage takes place, that will affect the d delta f part, that is the load part, because generation has not dropped. Generation is still generating 1260 megawatt, right? Because we have ignored the losses, so sum of generation is equal to sum of the load. So generation is still working at 1260, only load has dropped to 1200. So that's why for calculating D in the previous slide, I considered 1200, because obviously 60 megawatt hour was lost. But here I will calculate based on this value, because the generation has not dropped. Generation is still generating at 1260. You will see in the frequency value. Let us quickly calculate this. So this will be 2.5 by 1200. And because we have to keep the value 1 by R here, so let us calculate 1 by R. What is the value of 1 by R? It will be 1200 by 2.5. It will be, can you quickly help me out on that? So what is the value of 1200 divided by 2.5? It will be 4. It will be
2.08 by 10.
1200 divided by 2.5. What is the value?
480.
480. And what will be the dimension? Because it is 1 by R.
Megawatt per hertz.
Yes, it will be megawatt per hertz. So now you just have to put the value 480 here plus D we have calculated in the previous slide. What was the D value? It was, I think it was 36, right? We calculated 36. Yeah, D is the same, 1.5 of that divided by 1%. So this value will be 60 by 516, right? 516. What is the value of this frequency?
0.116 hertz.
0.116 hertz. And so eventually the F will be 50.116 hertz. Now, two observations you have to make from this question. One observation is basically just see in the previous example, if you observe, the frequency was more, right? It was 51.6 in the previous, when there was no speed control. That means it was 51.6 hertz. That's what I remember, right? Now when the speed governing action is there, that means the frequency increase is less than what actually this frequency would have increased. So believe you me, this 51 hertz is a very high frequency. 51 is not a good frequency, because 50 is our nominal frequency. At max you can go to 50.05. I think it is 50.05 or 50.1, not more than that. So here you are going till 51.6. So that is the value of frequency will increase if this droop characteristics is not there in the system. And as soon as you add the effect of the droop, you see the frequency has just increased to the 50.116 hertz. That is the importance of droop characteristics. I hope it is clear now to everyone with this question. Okay, now any queries, or shall we go ahead? Because I just need to complete, I have just 10 minutes remaining, so I just need to complete few more parts here and then we'll close. Any queries? Okay, if no queries, then I want to start the new topic here, that is fundamentals of AGC. AGC is automatic generation control. Now, just wanted to give you a hint here. What we are going to see is basically, now you have seen just now in the previous example, is if let's say there is no droop characteristics, that means the frequency will increase to 51.6 hertz, which was a very high value. And now if you add a droop characteristics, that droop characteristics is nothing but adding a primary load frequency control. After adding this primary load frequency control, you are seeing that the change in frequency is less, although it has increased, agreed, because load has reduced, it has increased. But even then, the frequency increase is lesser than the what could have been if the speed control was not there. But still frequency is more than 50. Now, we saw in the initial diagram that there are two loops. One is primary load frequency control loop and there is secondary load frequency control loop. Now, primary load frequency control loop was what we have seen till now. So basically, I adding a droop characteristic is changing the load change based on the damping coefficient. This is all for the primary load frequency control. Now, for the secondary load frequency control, the idea of secondary load frequency control was to bring the frequency back to the nominal value. So assume that this is the time, this is the frequency. What was happening, let's assume this was 50 hertz. In the primary frequency control, you saw that the frequency has dropped, agreed, if the load has increased, but it has dropped to a lesser value. This was happening in the primary frequency control loop, primary load frequency control. And now this AGC, the role of AGC is to bring the frequency back to the nominal value. This part is known as AGC or secondary ALFC loop, or this was the ALFC primary control, right? So this is what we are going to see in this probably just 2-3 slides, that what exactly how you will bring the frequency back to the normal value, which is nominal value, which is 50 hertz. Right, I hope it is clear what exactly you are going to see here with the example also and with this concept also. So in the primary loop, we saw that the load change or whatever change has happened is actually ensuring that the frequency deviations are stabilizing or settling at a value, which is this value. It is settling at a value. And this depends on the governor droop characteristics. Obviously, all the governor droop characteristics of the generators will behave in such a way that it will stabilize the frequency. And also the frequency sensitive loads. It depends on these two factors. This is what we saw till now. Now, the goal is for this AGC, there is another name for AGC is supplementary control action. And the goal here is to bring the frequency back to nominal value. This is the goal of this AGC. And how does it do that thing? It actually changes the load reference set point. So this is what we have seen previously, that if you want to change the R, the slope regulation, that droop characteristic slope is changed by changing the R. But if you want to shift the slope up and down in the vertical sense, so if you want to change the slope up and down, then you have to change the load reference set point. And this set point is changed by a motor. There is a motor in the mechanical sense, and this motor actually changes the reference set point for the generator. So there is a speed changer motor for this purpose. Right. So if you change the load reference set point up and down, then automatically the regulation, based on the regulation, whatever the generator is operating, it will automatically settle to a value which is actually exactly at 50 hertz, not at any other value. Right. The primary objective, I hope the concepts and the background is clear. Just to give you a quick idea again, or to recap this thing, that what is the primary objective of AGC is to bring the frequency back to the nominal value. That is the main objective. And the second objective, which will actually I'll be discussing first in the next class, that obviously in the power system, to control a big system. So for example, even in India, I'll just give this idea for so I'm just drawing a very simplistic diagram of India. So in India, there are 5 regions. One is northeast, east, north, west, and south, right? And you can imagine the size of the Indian grid, and there are a lot of power plants. To control this complete power plant is not very easy. So what they have done is basically for the control point of view. So there is for to control this big Indian grid, they have divided this into the multiple layers. So the smallest layer is state load dispatch center. So this state load dispatch center controls its within the state. So India is divided into multiple state. We in Roorkee, we are in Uttarakhand. So this is just for our foreign students. So India is divided into multiple states. So every state has its own load dispatch center that controls everything within the state, right? And then there is a RLDC. This is regional load dispatch center. So this 5 regions, east, west, north, south, and northeast, these are the regions. So individually there are states, and then the states control everything on their own. They try to control. If they are able to do it, that's perfect. If not, then the mismatch is passed on to the RLDC. RLDC is the regional load dispatch center. They try to minimize the mismatch or the error, or error in terms of frequency, error in terms of voltage, everything they try to compensate. Now, even then, if RLDC is not able to do it, then lastly NLDC is there, which is National Load Dispatch Center, and they try to control this interacting with multiple regions, right? So this is the way they fine tune the error. This is the way they minimizes the error. So basically, whatever mismatch I'm telling you here, between here there is some mismatch, there is some mismatch here. So there are actually, this complete power system is divided into control areas, and there are control areas. So let's come back to the AGC. The goal of AGC is to, obviously, if we have to minimize, if let's say state is unable to minimize the error, let's say some load change has happened within the state and the state is unable to satisfy that load change, so obviously that load change will be passed on to the neighboring region or the RLDC. So basically the goal of RLDC will be to minimize the change. So let's say if we talk about Uttarakhand and UP, let's say these are the 2 states which are neighboring state, Uttarakhand and Uttar Pradesh. So let's say if a load change is there in Uttarakhand, then obviously some power will flow from Uttarakhand to Uttar Pradesh, Uttar Pradesh to Uttarakhand. So now when this power is flowing, the goal of RLDC, Regional Load Dispatch Center, will be, if let's say Uttarakhand is unable to satisfy or minimize the error on its own, so it is taking help from Uttar Pradesh, and if it is taking help from Uttar Pradesh, that means it is passing on the mismatch to RLDC, that is Regional Load Dispatch Center, and if Regional Load Dispatch Center will try to minimize it, and eventually the goal of RLDC will be to, let's say there will be some delta P which will be required to satisfy this load. His goal will be to make this value equal to 0, so that the mismatch goes to 0. And this mismatch is actually known as interchange power. So the second objective of AGC is to minimize the interchange power between control areas and set that value to the scheduled values. That is the second goal. So interchange area and the nominal, to bring the frequency back to the nominal value. These are the 2 primary goals of AGC. Right? It makes sense to everyone? Now the last one, just quickly I'll close. The secondary objective of AGC is to take care of the economics, that whatever change, because obviously to satisfy the load change and everything, there has to be some generator which is compensating for that. And if that generator has to change its value, generation value, then we have to also take care of the economics of it. We cannot request a diesel based generator to satisfy that. It is easy and it is always available, but obviously diesel is costly, we do not want to do it. So that's why we also have to take care of the economics, and that is the secondary objective. Obviously first objective is to bring the frequency back to nominal value. Once everything is stable, then only you can focus of economics. If it is not, then you cannot consider about economics. So that is why this is the secondary objective. Right. So with this background, we will be seeing this AGC in the next class, and hopefully I'll finish the AGC part in the next class. So I'll stop here. If any queries, please let me know.